Hey guys, welcome to another exciting video of C++. In this video, we'll be having a discussion on what pointers are or how we use pointers in general. Now, pointers are something that C and C++ offers you that many other high-level languages like Java or C Sharp or JavaScript or Python, they don't give you access to, because they have something called as a garbage collector, and that's good. You don't have to depend on allocating and freeing all the memories by yourself, but at the same time you get the leverage of using pointers in C++ that can be used in many ways to optimize your code and make your code run faster, and also in many cases to do some tricks that you can't do with other languages in case of performance optimization. So without further delay, let's get started. So before we understand pointers, we need to understand the concept of variables. Now let's say we have a variable called int a and it has a value of 10. Now, whenever we consider a variable, there are three things that we have to consider. First, that variable, it contains a type, how the data should be treated. In this case, the data should be treated as int, because at the end of the day, the data is a binary stream of 0 and 1s. So you have to have a way to understand that data, to represent that data. And in this case, for a, it's an integer. And the second thing that a variable holds is a value. So in this case, that value is 10. But the third thing that a variable holds is where to store that value. Because without a particular place to store that value, whenever you need that value, how can you retrieve that value if you don't understand or know where the value is stored? And that particular location, in most of the cases, the particular cell or the consecutive cells of the random access memory of your computer or RAM, we're not talking about hard disk, because the hard disk is a very slow memory and it's actually not considered as a memory in case of runtime memory of a computer. So in case of runtime memory, we generally consider RAM. Now there are some other faster runtime memories like your cache and registers. They reside on CPU and they are much faster than RAM. But most of the things that are declared in your runtime, like the functions or the variables or this whole operating system, actually residing in your RAM. So whenever we are talking about memory in general, we are talking about RAM. So let's get back into the topic. So the third thing that a variable holds is memory location, and this memory location, we call it as a pointer. Like you are standing on a road and there are a bunch of houses, and you have a pointer, your index finger, and by it you are pointing to the house where someone is asking you like person A is residing at which house, and then you point that house with your index finger, your pointer, that that person resides at that house, and then that person goes to that house and meets that person. So at the end of the day, the pointers, they are actually let's say the house number of the variable inside your RAM. And in most of the cases, whatever the type of the pointer is, the pointer itself is a integer referring to a cell in your RAM, and that's all. So to get this three data out of a variable, we have different kinds of ways, but the easiest way of all is to get the value. You can simply type the name of the variable, and that is sufficient, because the name itself represents the value of that variable. It acts as a reference to the value. Okay, so the next thing that we are interested now is the runtime type of that variable, and we can't generally get that runtime type of the variable, but there is a easy way to get that. For that, we need to include a header file called type info. So type info, and inside type info we have something called as a type id. So we can use that function. So we can say type id, and inside type id we can pass that variable to get the runtime type id of that variable, and to get a string value of that we can use dot name. It will give us a string denoting the type of that variable. Now in this case, to format everything, I'm just putting a arrow here. And the third and the most important thing is the address where the variable is situated inside your RAM, that house number in your RAM. And to get that, we simply append an ampersand in front of the variable, and this returns us the address of the variable, the storage space where the variable is stored. So now if we run this program, you can see that the value of the variable, it's 10, and the type of the variable, it's int. And here we can see an hexadecimal number. A hexadecimal number is something in general, whenever we are talking about numbers, we talk about numbers that have 10 digits, that is 0 to 9. But a hexadecimal number, it has 16 digits, 0 to 9, and then also A, B, C, D, E, F. So this is an hexadecimal number referring to the first block from where this data has been being stored. And we can also use size of to get how many blocks this data is stored. So we can say, let's say we can give another arrow like this, and then we say size of A, and this gives us how many consecutive cells in the memory the variable is stored. So if we run this program now, we can say that A is an integer which holds the value 10, which is of type integer, and a variable of type integer, that is A, it takes 4 blocks of memory. These blocks, they are called bytes, and a byte simply represent 8 bits, and each bit can have a value 0 or 1. So in this case, this integer, it has 4 bytes, they are consecutive, and the address of the first byte, the address from which this memory starts, is this. So what our computer or the compiler does, or the program does, is it goes to this location in your RAM. Let's say your RAM has 1, 2, 3, 4, 5, 6 such cells one by one, and at this particular cell, it starts reading a stream of the 1 and zeros. So whatever it's there, and it reads up to 4 bytes, that is, it reads up to 32 bits to find out what is the value, and it gets the value as 10. So what is a pointer? A simple answer to this is a pointer. A pointer is nothing but an integer, which is actually the address of your variable inside the memory. So how do we declare a pointer? The next question should be this, and that is, we simply put an asterisk in front of the name of the variable when we are declaring that variable, not when we are using that variable. Whenever we are declaring that variable, this asterisk defines that this is a pointer. Now you can use this asterisk like this, it doesn't matter. Only thing that matters is that at the time of declaration, let's give it as a underscore ptr, denoting that this is the pointer to this variable or this memory location A, and asterisk in between the declaration of the variable and its type declares that this is the pointer to a memory location, and we need to read that memory as an integer. That's all. So here we already know that this represents a memory location, this is the pointer. So all we can do is we can initialize this pointer as address of A, because this pointer at the end of the day, it holds the address of A. Okay, so now how we can use a pointer? So like the previous time, to get the data of the pointer, we simply put an asterisk in front of the name of that pointer, and we give the name of the pointer, and this, it's called dereferencing, because a pointer, it's the reference. Now here A is a variable, and this pointer is also called a reference to A. It denotes to the memory location, and now a pointer, it's being a reference, we need to dereference it in order to get the value, and to dereference it, we put an asterisk in front of that pointer. Now here this asterisk is used to define that this name is a pointer, this name denotes to a pointer, but this asterisk defines that I don't want to get the address or the value stored in the pointer, but I want to go to that pointer, that memory location, because pointers at the end of the day, they are just memory locations. They are just ordinary integers that refer to the house number of the variable that resides in your RAM, and this asterisk says that I don't want that house number, I want the person inside that house number. So it gives the value of the pointer, and then to simply get the address of that variable, we just simply can use that pointer here directly. So you can say a underscore ptr, and it's going to give us the address. So think of this situation like this: a pointer, it's opposite to a variable. A variable by its name defines its value, and when an ampersand is used in front of that variable, defines its location. But a pointer by default, by its name, defines the location, but whenever an asterisk is used in front of it, it defines the value. Okay, so now if we run this code, we can see that this pointer aptr, it has this, it stored this the actual value that this aptr hold is not 10 but this integer, this memory address, and we can see it here. And by dereferencing this memory address referred by this pointer, we get this 10. So it's actually very simple if you consider it in this way. So now let's talk about arrays. Why? Because arrays and pointers, they're basically same. You ask me why? The simple answer is this: if I put this asterisk off and if I put a 0 here and I run this code, you will see that it gives me the value actually stored into the pointer. I don't need to use that asterisk, I can use this 0. Yes, whenever we declare an array, that array is stored into the memory, that is your RAM, in a contiguous order, that the data is stored one after another, and the name of that array, it actually is the location, or in our case the reference or the pointer. That pointer points to the first element of that array, and so technically whenever we are using array, we are just declaring a pointer to a contiguous block of data, and we use 1, 2, 3, 4, 5 as offsets to get the I plus 1th data. Now why I plus 1th data? This is not actually code, but just imagine this: we have an array and it has it's of type integer, and it has 3 elements, let's say 10, 20 and then 30. And now, as I have told you, and it's of size 3. Okay, and now as I told you, this array, it's actually a pointer to the beginning of that data. Let's see, we put an end line here and we see out only the array as a variable, not giving the index. So let's run this code to find out, and it's actually a memory address. So all an array is by its name is a pointer to the first memory address. Now there is something called as pointer arithmetic, and we can simply look into that via traversing this array. So what I want to do is I want to get to the third element, and to get to the third element I need to go to the pointer that points after this value is stored. That is, I need to go 8 bytes, because integer is 2 bytes, so 8 bytes ahead of this memory location. And by pointers, because this pointer is an integer pointer, although I am declaring an array and as pointer is the same, so this pointer I can say +2 to say that okay, you are at this memory location, now go 2 more houses ahead, and those houses can store 1 integer each. So I am not giving the size of integer times 2, but just +2. But the compiler is smart enough, or the program is actually smart enough to understand that I am going to go add 2 integers, not 2 bytes or 2 bits. Okay, so don't confuse that this means 2 bytes ahead. or 2 bits ahead, it actually means that I want to go ahead to size of 2 integers. That means this actually represents size of int times 2. By these two I am actually meaning this, and this is simply a pointer arithmetic, and what it should give us is the same output as array index 2. So let's do it and check it out. And you say, no brother, this is not that same output, this is and memory address and 30. It's right, because I did a simple mistake. I tried to print out that address, not the value inside that address that I told you earlier. To get the value inside that address, I need to dereference that address. Okay, even I can dereference this address also like this, and as this is a pointer, it will give me the value. So now run this code and look. So by dereferencing this address, I actually converted this into the output called 10, and by dereferencing this address, that is array times array plus the address at array, and then going 2 blocks of addresses ahead. By 2 blocks I mean 2 integer size blocks. We get to the address where the 30 is stored. So when we dereference that address, we get this, and the same output is derived as array plus array indexed 2. So I hope in general this gives you an idea of what arrays and pointers are. Basically they are same, just the style of declaration is different. And one more thing, whenever you declare an array, in general array is declared as in the stack of your RAM. Now your RAM, it has 2 slots, one is called stack and one is called heap. Now it's not like that you have a particular boundary where the 2 slots are divided, but let's say it's like this. Your RAM, it can be considered as a long one-dimensional scale, and at one end of that RAM starts a contiguous memory allocation. That means whatever is allocated will be after the last allocated memory, and this continuous segment of memory is stacked because the memory or the variables or the functions, they are stacked onto one another. Even your most of the system calls and your everything that you are doing in general, they are stored into the stack. And there is another part where we have some memory here, some memory there, some memory elsewhere, and it's called heap because the memory, it's not organized. A common implementation of this heap is your linked list, where you have linked to that next element that's somewhere else in your heap. And in general, whenever we declare an array like this, it's declared in the stack. But let's say we want to declare a dynamic array in the runtime, and for that we declare the array in heap. Now a very common way to do that is using the new operator. So we say int array, and in this case we usually create those arrays as pointers, and we say it's of a new array of size 3, new integers of size 3. And what it will do is it is going to make me a pointer to a memory what is going to be allocated at runtime. So I can simply use a variable here. Even we can use new int of a, so it will create me an array of size 10. Okay, but you can't do this like here, because this memory, the compiler needs to know this at compile time, because it's going to be allocated in your stack. But this memory, the compiler knows that it's going to be allocated at runtime, so it can take the variable that was there when the program executed, and it can take that value, and it can allocate the contiguous memory, the same contiguous memory in the heap portion, and give you a pointer to it. Even what you can do, you can say like this in languages like Java, because in that cases the only pointers that you have is actually arrays. But the old way, what we used to do is we used to call a function called malloc. And what malloc did, it allocated a memory size of the size provided inside these curly braces. So in this case, I want to allocate a memory which is of size, size of integers times 3. Okay. So let's call this an array as array2, and it's going to create a void point. It's going to allocate this memory inside the heap, and it's going to give you a void pointer because it doesn't know this malloc function. It has allocated these many houses for the size of houses. So this actually implies as 4 times 3 the size of houses, but it doesn't know that what kind of data is going to be stored into that house, because this is an integer and this malloc, it returns a void pointer. So to fix that, we simply used to give an int pointer here to say that this is the memory. I want to initialize this memory like this, and then what I could do is I could simply run a for loop. And then I could initialize these values like this. Array 2i equals to array I. And then I could simply print the values of array 2. Just I will get this loop once more, and I will see out. Array 2i, then a comma. Okay, and here also I need to put an end line to get this value into a new line. Now if I run this code, you can see that this memory is actually created on the heap, and I can also free this memory and create a new memory and allocate that to this memory. Now there are two ways to deallocate or free this memory. Freeing the memory is just as same as deleting that pointer. Okay, deleting that variable. Whenever you are not using normal variables, what happens is that this is the scope of main. These curly braces, they denote the scope of that variable. The scope is where the variable gets created, and when the scope ends, the variable is automatically popped out of the stack. That means that variable is automatically deleted. But whenever you declare a memory like this using malloc or new, you need to free that memory by yourself. So what we will do is we will be using something called as a free, and this will take the pointer to the initial block of that memory, and it will free that memory just like this. So this is how we can simply deallocate the memory that was allocated by memory alloc function malloc. So let's get this pointer. And in C++, there is a slight difference. To free a single value pointer, what you can do, a single pointer, know that there is only one value stored in that pointer inside that memory, and you want to free that memory. So what I can do is I can say delete, and it will free that memory. So that memory is released. In this case, A will be released when this scope is over. And also to free an memory that is contiguous and that is an array, we just simply say the same thing, but after delete we give this braces to say that this is not a single memory, but look into the memory till which this contiguous memory is stored. So this is how we typically use pointers in general. I hope this helps you to understand pointers a little bit better. And in pointer arithmetics, there are a few operations that you can use. I will be ending this video after discussing that. The first thing we have already seen is plus operator that allows you to traverse to the size of the houses or the type of the variable times the arithmetic number specified here. And also the same way you can traverse in reverse direction, because RAM is one dimensional storage where the data is stored. So by this I will be traversing in the reverse order. So these are the basic arithmetics that you can perform on pointers. You can dereference a pointer or move that pointer forward or backward by adding and subtracting values from that pointer. And that's about it, what you need to know about pointers in general. So I hope that this helps you in understanding pointers and getting hang of the pointers. But there are some other things in C++ like the smart pointers. We will be covering those things in a later video, and they are nothing but they are some classes that were written on top of pointers in order to help us by managing this delete, and by giving us a way like the garbage collector that Java has or any other language has, to make our lives a little bit easier. But whenever we are using smart pointers, there is a drawback, and that is the overhead that's going to be caused by those smart pointers, because they are going to call some functions and then they are going to operate on the pointers. So obviously they are going to be much slower than the raw pointers that we discussed today. So hope this helps you. Hope you have enjoyed this. See you next time. Bye.